All right, so this
Okay.
video is a demonstration on how to use the proof of concept developed by Envisol and in.mat-Lab on a project called 3D Maint.
Okay, so the first thing we are going to do is to import our data, our dataset. Our dataset should look like this kind of file. So here, as you can see, we have one row per sample. Each sample should be described by the grade of the sample, its different physical properties, the depth at which it was taken, its coordinates. So here it's in longitude and latitude, and it should also have an ID. So once you have a clean file like this, you can start importing it into the software.
So a small precision is that it needs to be in a CSV format.
Exactly. So here we can see the importing interface. So first, as you've seen, I've imported the file by navigating in the Explorer. And here you can see that you have to choose which of my column names correspond to which parameters. So most of the time it will do, the software will do it on its own. So it will just detect the name of the column and match it with the corresponding feature. But sometimes, such as for this one and this one, you have to do it manually. So you can scroll down the list of columns and choose the correct column name. Once that is correct, we need to check that the EPSD code is correct. So the EPSD code corresponds to the coordinate system in which your data is imported. So here I'm in longitude and latitude, and that corresponds to an EPSD code of 4326. We also have one more thing to check. It's whether or not our Z column is in relative depth. So it's depth under the surface of the soil, or if it's in a meter above the sea level. If it's in relative depth, you can check, you can let this checkbox checked. You can leave this checkbox checked. Okay, so once all of this is correct and has been checked, you can import it. This can take a while, and while it's importing, you can continue by importing the other files we are going to need. So the first one you can import is the topography file. So it's going to look very similar to the structure of the data file. It needs to be also a CSV file, and it needs to look like this. All right. So you need 3 column minimums, the longitude and latitude of each point, as well as the elevation in meter above sea level of the point. These do not need to be the same ones as the points in your data file. This can be a separate file. Once you have this file in a correct format, you can select it here. So there we are. And just as before, you need to check that all the columns are correctly selected and that the EPSD code is correct. Then click import. All right, so now our data import is done. So this is the data points we have imported in the interface. And now we are going to define the limits of the model of the modelization we want. So by default, it creates this rectangular limit. As you can see, it's very wide, and it's going to encompass all of the data we have. However, it's not always the best choice to leave it as is, because you will need a more you will need to be maybe a bit closer to the data to have a better model. Obviously, here you won't have a lot of information, so the model won't be very accurate, and maybe those points are just too far away, and this point is too far away to be accounted for by the model. So we are going to create a limit that is much closer to the data. So as you've seen, I clicked on the edit, and now I'm just creating a polygon around my data. So once I'm happy with how it looks, I can just right click, and now I have the new limits. I can modify it if I want. Here I can add a point if I want to. And once I'm happy with it, I can just click validate and have my new data, my new limits. Once I'm done with the data import, the site limits, and the topography, I can create the grid. So while this is working, we can import the third file we are going to need, which is the reference file. The reference file is going to contain a list of reference that might be useful. All of those references need to have a few information. Okay, so the necessary ones are all of those. All right, so here, as you can see, we have an ID that needs to be unique. This will be the one that will be displayed in the software. So it needs to be unique so that you can choose it accurately. Then you have here the application corresponding to the reference, the grade, the reference, the grade of soil the reference is referring to, and then here the parameters, the physical parameters of the reference. Once this is done, you can import it. Oh, and this file is a CSV as well. Here it's the same. You need to choose the few fields that haven't been correctly identified. And yes, we can import. All right. And the grid has been finished as indicated by this tick. So we can choose a reference, this one, and then we can start the modelization process.
So basically what it does is that the model will generate a 3D view of the adequacy of the data points relatively to the reference given. So this is what we'll see here with a value modelized between 0 and 100%. So 100% means that the value acquired on the field states a perfect adequacy relatively to the reference. So the properties of the materials are perfectly fine for that use. And then 0% means no adequacy at all. And you have that gradient between 0 and 100%. So you can see how in a block model of the mine or of the project, you can see how especially you have materials adequate or not to the reference.
Yeah, that's the first model. And we have a second one that is right here. And it's not exactly the same. So, Antoine, if you want to...
Yes, in that case, it's much more precise, as it will give you precisely where you are perfectly certain that the material is above reference, and you'd have those 4 grades of downgrading. So it can look similar to the simple grading model, but in some cases this would be more reliable, as it's not based on the same mathematical hypothesis and modelizations. So that's an additional indicators of the adequacy.
I'm just going to go back to the preview here because I prefer the color for the demonstration of the visual manipulation you can get with this type of block model. So here, as you can see, my model has 100% opacity, which means it's not transparent. But if I want to see what's happening inside my block model, I can assign it a great opacity, and that way I have a vague view of where my hotspots are. So that's the first way of seeing inside the model, and the second one is going to be by slicing the model. So for each direction, so X, Y, and obviously depth, we are going to have these slicers. So for instance, if you want to slice the model in the X direction, you can just click here and we'll only give you the 1st to 25th row of the model. So it can take a little time because it's quite computation heavy at the moment. All right, I'm just going to, since we're doing this, I'm also going to get this here. That way we just have to do it once. Yes, and let's see. There we are. So as you can see, I've just cut the model here and here. And if I do this, I can see what I couldn't before, meaning there is a hotspot. Well, there is a spot of higher adequacy right here. And it's also nice to be able to just go through the model layer by layer, just to see what is happening once you have a good idea of what your model is like. Yeah.
And you have some additional properties that we have not yet implemented in this proof of concept, which is volume calculations. Once you've seen how spatially it is correlated, you can obviously calculate the different volumes relatively to each references, and then a potential report as well regarding the adequacy. So please keep in mind that it's fairly easy to use, fairly quick to use, even though we've seen some slight delays. So once you've seen that reference in particular, 03F2, you can go back to site and choose another reference, so another usage of the materials, and restart the processing and see how it works relatively to the data you have from the field.